And now the final technique we need to learn uses an algebra concept called partial fraction decomposition. You should be familiar with partial fraction decomposition. It's a way of breaking down rational functions into simpler rational functions. So a single fraction into multiple fractions added or subtracted together. This is a very basic algebra concept, which you should have learned somewhere in algebra. I know the primary place where it's taught is pre-calculus. I will include a link to my full partial fraction decomposition algebra lesson in our course so that you can go back and review it if you want. I'll go over a real basic review of it here, and we're going to do a bunch of examples, but if you need more, I will give you the full rundown, a link to the full rundown in our course. All right, so let's look at a particular integral right here. This integral should look familiar to you in that we have looked at integrals like this before, not this specific one, but ones like this before, and we've used completing the square to try and integrate it. dx, or 1 over a square root, or sorry, 1 over the quadratic trinomial. Okay? Now, the problem is completing the square is not going to work out as nicely as it did in the past. But we'll still be able to use it, and we could do trig substitution to help integrate this one. It's not going to be easy. It looks a lot like the example I gave you at the end of the trig substitution lesson where there is no square root, but it can be done. However, an easier way to do it is that algebra technique of partial fraction decomposition. So I'll give you a quick rundown of how the trig substitution would get started. And then we're going to talk about partial fraction decomposition, because we really wouldn't necessarily do this problem using this trig substitution. So first off, we look at x squared minus 5x plus 6, and we're going to complete the square. So we have x squared minus 5x. I'm going to add the negative 5 divided by 2 squared to this. Well, if I do that, I also subtract the negative 5 over 2 squared, and I still have the plus 6. So then what happens here is that this is factorable as x minus 5 over 2 squared. And this piece ends up being whatever we get. So what's this? This is 25 over 4. 6 is, and that's a negative because it's right here. And 6 is 24 over 4. So we're going to get negative 1 over 4. Okay, so then we can replace that into the integral and say we have dx over x minus 5 halves squared minus 1/4. Now, if this were a plus, this would be an arctangent integral. You would have something in the form of du over u squared plus a squared. And it would be arctan. And this is something we talked about when we were doing this back in the inverse trig section, is that in order for this completing the square to work out perfectly to turn into one of our inverse trig functions, it really hinged on this number right here, which affected this number here. In this case, it didn't work out nicely because that's not a plus, it's a minus. And so then that brings up the idea of trig substitution, in that if I look at this, I could say this is u squared minus a squared. It doesn't have the square root on it, but remember we talked about how you don't really need the square root. U is this right here. A would be, and this is a squared, would be a half. And so if you use this substitution, we know that for the square root of u squared minus a squared, we use that u has to equal a secant theta, so that the square root of u squared minus a squared could equal a tan theta. Now, in this example, that would tell me that u, which is x minus 5/2, should equal 1/2 secant theta, and then then dx could be found by just moving the 5/2 to the other side, or even still just differentiating both sides. The 5/2 would go away anyway, giving us dx. And the square root, or in this case we don't have the square root, in this case x minus 5/2 squared minus 1/4, which is u squared minus a squared, should equal a squared tan theta, a being 1/2, so let's replace that with 1/4. So we could do the substitution. Let's just fill in dx. The dx would be, what, 1/2 secant theta, tan theta, d theta. So we can make all the substitutions we want. Dx is here, that would go here. The denominator is this, that'll go there. Do the integration, etc. So we can get it done with trig substitution. It's a whole deal to get it done, but it can get done. But it's not the likely way we would do this, so I'm not going to finish it. What we're going to do instead is partial fraction decomposition. Much simpler algebraic technique for something like this. Now, the concept of partial fraction decomposition is an algebra concept. The idea is really simple. If I had 1 over x plus 1 plus 1 over x plus 2, and I had to add those fractions together, everyone should be able to do it. You'd find the common denominator, which would be x plus 1 times x plus 2. So we multiply the first one by x plus 2 over x plus 2. You would multiply the second one by x plus 1 over x plus 1. You would then add your numerator straight across, giving you 2x plus 3. And you could multiply out this denominator, giving you 2x plus 3 over, what would that be, x squared plus 3x plus 2. Pretty easy. Okay, no big deal, something everyone should do by the time you get to Calc 2 for sure. Partial fraction decomposition is that in reverse. We start here and we decompose that into this. Now, the key to being able to do that is that this denominator is factored into these two factors. And each of those factors is the denominator of these two fractions. And so if we're going backwards, we'll know that that's what the denominators have to be. The question will be, well, what are the numerators? And once we figure out what those numerators are, in this case they're 1, but if we were going backwards we wouldn't know what they are. Once we figure out what those numerators are, we have the decomposition. Now it's in some way related to this 2x plus 3, but you see the 2x plus 3 and the 1. There's not really an easy way to get back that way. So that's the whole process we'll need to go through with partial fraction decomposition to go back. So in order to properly do partial fraction decomposition, the first thing you have to make sure you're dealing with is a proper fraction. As far as rational functions go, a proper fraction is when the numerator's degree is smaller than the denominator's degree. If it is not, then the way you would have to get started is to create a proper fraction, and you would do that by dividing. So if you start here and this isn't a proper fraction, you would actually do this division, which would result in a quotient being some polynomial, and then your remainder over your original divisor. This fraction right here will always be a proper fraction. And then we would look to rationalize once we have a proper fraction, the next thing we're going to look to do is to factor our denominator completely. And your factor in your denominator will always break into either a linear factor or a quadratic factor. Now those factors might be raised to different powers, but the factor itself is either going to be linear or quadratic. If we have linear factors, what we're going to do is we're going to look at those linear factors as denominators of separate fractions. And since the original fraction we are working with is a proper fraction, the resulting fraction should be a proper fraction, therefore making the numerator a constant, because again, the degree of the numerator has to be smaller than the degree of the denominator. So this would have to be a constant over this linear factor. The question is, what constant would that be? Also, if you have a repeated linear factor, so that factor is raised to a particular power, you would have to address that in the problem by placing that linear factor to the first, then that linear factor to the second, all the way up to that linear factor to whatever the highest power is, as separate denominators throughout the decomposition process. However, since they are all linear factors, the numerators would still just be constants all the way through. We'll see an example of that. Then the other possibility is we have quadratic factors. So if we have a quadratic factor, it could look something like this. It could be raised to the n. First off, that's going to be one of my denominators, in which case we would have to look at what the numerator would be. Well, again, if it's going to have to be smaller, because this has to be a proper fraction, that numerator could have a linear term and a constant term. So it's a little bit bigger now because the denominator is bigger. So we write it as capital BX plus C, in which case B and C are constants that we would need to find. This one should have another B. It should say B2X plus C2. There's a little typo there. And similar to the linears, if that quadratic is raised to a power, we would have to have one denominator be that quadratic to the first, then to the second, to the third, to the fourth, up to whatever the highest power is. But still, since it's a quadratic factor in itself, the numerator continues to keep the same form of bx plus c. But they would be different b's and c's in each case, just like here would be a1, a2, a3. This would be b1, c1. This one would be b2, c2, bn, cn, etc. And what you're doing here is you're laying out what the possible fractions could have been to have given you that single fraction when they were added and subtracted together. So let's see an example. So here's that original integral we were talking about. So let's look at the fraction 1 over x squared minus 5x plus 6. This fraction could be written as 1 over x minus 2 times x minus 3. And the fact that the denominator can be factored is the reason why partial fraction decomposition will work. So you need to be able to factor your denominator as much as possible. Don't just factor it a little bit, factor it completely. Also notice that the original fraction is a proper fraction to start with. So this tells me that if these are the factors of the denominator, then the two fractions that added together to give me this single fraction here, it had a denominator of x minus 2 and a denominator of x minus 3. So that when I found the common denominator between these two fractions, I got this. And these are the only two denominators that could have possibly given me this common denominator. So then that tells me, since they're linear factors, the numerator here is a1, the numerator here is a2. Some people like to write them as a and b, so that they're completely different letters. It doesn't matter. They're just holding the place of some constant you need to find. I prefer A1 and A2, but you can do whatever you want. All right, so then what we're going to do from here is we're going to look at this equation that we just created, and we're going to try and solve it so that we can figure out what A and B equal. So first thing I'm going to do is I'm going to clear out the fractions. I'm going to multiply by the common denominator across this entire equation so that I don't have all this fraction business. Well, the common denominator is sitting right here. If I multiply this whole fraction by that common denominator, it cancels and gives me just 1. If I multiply this fraction by this common denominator, the x minus 2's will cancel, giving me a times x minus 3. And then the final one would be b times x minus 2. So this is just a simplified version of this bigger equation. Now it comes time we need to find a and b. Well, there's a simple little trick we can use when it comes to these linear denominator factors. And that is to let x equal a 0 of each one of these factors. So let's let x equal, say, 2. If x equals 2, then this becomes 0. And if that becomes 0, this whole thing drops off, giving me simply that 1 equals a times 2 minus 3. So 1 equals a times negative 1, so a equals negative 1. And then I'm going to do that again by letting x equal 3. So let's get rid of this. And so we would get 1 equals b times 1, because now this is going to equal 0, dropping this off. And this tells me that b equals 1. So now what this tells me is, if I use that here, then I'm going to have negative 1 over x minus 2 plus 1 over x minus 3. And this is equal to this. So now when it comes to the integration, if I was to integrate 1 over x squared minus 5x plus 6 dx, I could instead integrate negative 1 over x minus 2 plus 1 over x minus 3 dx. Well, why is that going to be better? Well, it's going to be better because this is a pretty easy integral. So is this. Those are logarithm integrals. So I get negative 1 log of x minus 2 plus log of x minus 3. Throw a plus c on there. I could put these two together as a single logarithm, since this one's being subtracted or has a minus 1 times it. This one would be divided. So I could write this as log of x minus 3 over x minus 2. I'm just using my log properties, when to subtract logs, when you add logs, and kind of doing it in reverse. Usually you would expand something like this, but then we're going to contract it back down. So there is my final answer. And we got there through this concept of partial fraction decomposition, which largely, it's a lot of work, and it's going to get longer. But largely all this basic algebra, something you could have done when you were sitting in Algebra 2 class. Okay? We just use it to help us integrate. All right, this example is a little bit larger than the last one, but same idea. First off, I never look to do partial fraction decomposition first. Is this a simple just u substitution one? Well, no. The only thing you really should let u be would be the denominator, and the derivative of that is not this numerator. So I don't really see a u substitution working out right away. So then I go, all right, well, it's a rational function, right? Polynomial over polynomial. It is proper in that the degree of the numerator is smaller. Can I factor that denominator here? Well, sure, I could pull an x out. I would be left with x squared plus 2x plus 1, which I could then write as x times x plus 1 squared. Again, factor completely, that is. So what I'm going to do is try decomposition. Everything's there to allow me to do it, so I'll try it. So I have 5x squared plus 20x plus 6 over x times x plus 1 squared. So that tells me, based off of these denominators, is that one denominator should just be x. Another denominator should be x plus 1. And the final one should be x plus 1 squared. Now this is the one that always messes people up. And what's the reason why we have these denominators? Okay. Remember, the reason why these are the denominators we use is because we say this is the common denominator. What fractions would I need so that I could get this common denominator? Now, technically, I could just have this denominator and this denominator, and I could get this common denominator. That would be true. However, what we need to do is put every possible denominator that could be here that could still get us that common denominator, because we don't know what fractions we added together to get this fraction. So we have to list out all the possibilities. Well, while these two combined could give me this common denominator, all three of these combined could also give me this common denominator. And that's the maximum amount of fractions that could come together to give me this common denominator. And that's what we're doing here. We're placing the largest number of possible fractions that could have been added together to give me this single fraction. And so now we look at the numerators for each one of them. This is a linear factor, so here we get a1. The next one's a linear factor, so a2, a constant. And the last one is a linear factor, so a3. While this is raised to the second power here, the factor itself is still linear, so we still use a constant in the numerator. And now all we have to do is solve for these three constants, and we have our answer. And so what we're going to do is clear the fractions out of this equation first. Basically multiply everything through by this common denominator. So if we multiply the left side by that common denominator, we would just get 5x squared plus 20x plus 6, because it would cancel the denominator. If we multiply this fraction by the common denominator, the x's would cancel, and I would get a1 times x plus 1 squared. If I do it for the next one, I get a2 times x plus 1, and the last one would be a3 times x. Now I'm going to use the same trick I used before. Since the factors I'm working with are linear, I will let x equal -1, and I'm also going to let x equal 0. Those are the two factors I'm working with, x and x plus 1. They would each be 0 when x is -1 and x is 0. So what does that do? Well, on the left side, if I plug x equals -1 in, I'm going to get 5 minus 20 plus 6, so that's going to give me 9. -9. Then on the right side, anything with an x plus 1 in it zeroes itself out. So that'll be 0, that'll be 0. The only thing that won't have a 0 would be the a3 term, so I'll get a3 times -1. That tells me a3 equals 9. Okay? Then x equals 0. Well, if x equals 0, the left-hand side becomes 6. The right-hand side, anything with the x in it, which is here and here, becomes 0. So I'm just left with the a1 term times 1 squared. So you see a1 equals 6. Okay? So I have a3, I have a1, but I still don't have a2. So there's a couple of ways we can get a2. Here's the simplest way to do it. simplest way to do it is to say, all right, let's just continue this process. We already know what A3 and A1 are, so we could plug them in here and here. If we then continually place an extra x value in that we haven't chose yet, at random, it doesn't matter which one, something easy, let's say x equals 1. So we have A3 to be 9, we have A1 to be 6. What do we have left? Well, the only variable we would have left in this whole thing would be A2. So if x equals 1, the left-hand side becomes 31. The right-hand side becomes A1, which is 6, times 1 plus 1 squared, plus A2 times 1 plus 1, plus A3, which was 9, times 1. And if you notice, the only variable here is A2. So solve for A2, now you got your answer for that. So what are we going to get here? This is 2 squared is 4, 4 times 6 is 24, this is 9, so 24 and 9 is 33, subtract it, we're going to get minus 2 equals A2 times 2, so A2 equals negative 1. All right. So in the end, the integral we want to do is not this integral, but this integral, which would be 6 over x plus negative 1 over x plus 1 plus 9 over x plus 1 squared dx. And we still have to do that integral, but at least it's easier to do. This can be done with a logarithm, this can be done with a logarithm, and this will end up being a power rule integral. So now let's do that. So we have 6 over x minus 1 over x plus 1 plus 9 over x plus 1 squared dx. Again, this one here, when we integrate it, will be 6 ln of x. This one will be ln of x plus 1. And this one we're going to need substitution. We're going to say u equals x plus 1, du equals dx. The 9 comes out as a constant multiple, so we end up with dx over u squared, which in the long run ends up being, du over u squared, ends up being u to the negative 2 du. Okay? And once we do that, bring this up, we end up with a power rule integral. So add 1 to this power, divide by, so negative u, which was x plus 1, to the negative 1. Throw a plus c on the end, and we have our answer. And just real quick, why this one's a logarithm. Again, it's really actually a substitution. And it's the same substitution we use here. If you notice, this is u, and this is du. So du over u is your basic logarithm integral. All right, we have to clean up our answer a little bit. What I would do here is I bring the 6 in as a power using my log rules. The minus between these two logs means I should divide the things inside the logarithms. So I end up with log of x to the 6th over x plus 1 minus 1 over x plus 1 plus c. And that would be the best answer I could give. Throw an absolute value on the logarithm. Here's another one. Again, don't look to do partial fraction decomposition right away. What I'm going to do is look to say, is there anything else I could do here? Right? And there isn't, right? There's nothing here. There's no substitution that'll work. There's this rational function is just kind of a mess. But what I can do is say, technically the denominator is a 4th power. The numerator is a 3rd power. It is a proper fraction. And I can factor the denominator. Now, it's already factored, but not completely. So what I'm going to do is I'm going to factor that completely, and then I'm going to try partial fraction decomposition. In which case, I am going to factor this a little more, pull out an x, I have an x minus 1. This is a sum of squares, which actually can't be factored anymore. So now I have 2x cubed minus 4x minus 8 over x times x minus 1 times x squared plus 4. And so I'm going to end up with 3 denominators. One is an x, because that's this factor. One is an x minus 1, that's this factor. And the third one is x squared plus 4, which is this factor. But notice, this one is a quadratic, and these two here are linear. So that's going to change the numerator. None of them are raised to a power. The factor themselves are all first power factors, so we don't have to repeat anything like we did in the last example. So I'm going to say a1, a2, and bx plus c. So there are 3 variables we need to find in order to do this integration in the end. And this is what we're going to end up integrating. A1, A2, B, and C is what we're looking for. All right, so what do? Clear the fractions. Okay, here's your common denominator. Multiply the entire equation through by that common denominator. It makes the left side turn into 2x cubed minus 4x minus 8. And it makes the right side turn into a1 times, well, the x's will cancel, so then I'll be left with x minus 1 times x squared plus 4. Then a2 times x times x squared plus 4. And then bx plus c times x plus 1. Ooh. That's messy. Let me see if I can fix that. I'm running out of room here. That's the problem with these. They take up a lot of paper, a lot of space. These are long, big problems. But if you take your time, you can do it. So x times x plus 1. All right. Or minus 1. I don't want to mess that up. All right. So we do have a couple of linear factors here and here. So I'm going to start this the exact same way I did before. We're going to let x equal 0. That would be when this factor equals 0. And we're going to let x equal positive 1. That's when this factor will equal 0. And so when x equals 0, the left side of this becomes negative 8. The right side of the equation, anything with a singleton x factor in it, which is here and here, all zeros out. So this zeros out, this zeros out, giving me just the a1 times x minus 1, so that'll be minus 1 because x is 0, and 4. So this is negative 4, divide, you're going to get a1 to be 2. Okay? Then x equals positive 1. Well, again, put it on the left-hand side. You're going to end up with, what, 2 minus 4 minus 8, so negative 10. And on the right-hand side, anything with a x minus 1 in it. Oop, I didn't want to do that. Here and here, that zeroes out. So the only thing I'll be left with would be a2. So a2 times 1 times 5. And then you see you end up with a2 equaling negative 2. All right. Now we have b and c still to go. Now this is where things change. This trick we were using for the numerators above the linear factors, here and here, was to let this denominator be 0, that's the x we chose, and this denominator to be 0, that's the x we chose, and we were able to solve for a1 and a2. But when it comes to b and c, can't do that. This actually never equals 0. So there's no more x's that'll just give us b or just give us c. So there's a couple ways we can do it. One way is to try and work with systems of equations. That can get very complicated very quickly. So we're going to avoid that. the way I like doing this, and students tend to grumble about this, but it definitely is the less complicated way of doing it, is to do what I call the equal parts method. Now, this is not an official term, but I call it the equal parts method. And the idea is this. You have two sides of an equation. You have this side of the equation, and you have this side of the equation. And they have to equal each other. So whatever parts correspond to each other have to be equal. And what that means is, on the left side, I have a 2x squared. 2x cubed. And then on the right side, I'm going to have an x cubed. And whatever the coefficient is in front of here has to be equal to the one on the other side. And I'm going to use that to help me find b and c. That's why I call it the equal parts method. Now, in order to get to that point, here's the part that students grumble about. I have to multiply all this out and collect any like terms. It's not as bad as it seems, so let's get going. Let's look at the first one. Multiply these out here, and then the a1 goes into that. Well, let's see. This will be x cubed minus x squared plus 4x minus 4. And then the a1 has to multiply into that, so I end up with a1x cubed minus a1x squared plus 4a1x minus 4a1. Okay? Then I'm going to do the next one. Multiply this one out. I can multiply this one a little quicker. It's going to be a2x distributed in here. So I'm getting an a2x cubed. What I'm going to do is going to stack that underneath this other x cubed, because I'm going to end up grouping these like terms. And then I'm going to have a 4a2x. And I'll stack it under here. So what I'm doing is I'm organizing my like terms as I multiply out. So I'm doing two steps kind of at once here to make things easier on me. I think this organization really makes things go faster. All right. This one here is x squared minus x, and then the bx plus c has to distribute into that, so I end up with a bx cubed. I end up with a b minus bx squared. I end up with a cx squared and a minus cx. Again, kind of stacking it over the like terms. Cubes, squares, x to the first, and then my constants here on the end. So what I'm going to do now is realize that on the left side, I had 2x cubed minus 4x minus 8. So when I group this together, I get this, a1 plus a2 plus b x, and then I'll get negative a1 minus b plus c x squared, and then I'll get, I'm running out of room here, but we'll do it, 4a1 plus 4a2 minus c x, and finally minus 4a1. I really would prefer to do this on a much bigger space, you know, the nice big whiteboard in a classroom, but we make do. All right, so here we go. I'm going to start a new slide in a second, but let's just sum this up. This was the x cubed term. This is the coefficient in front of the x cubed on the right. This is the coefficient on the left. They have to equal each other. Same thing goes for the x squared. So that'll have to equal 0, because notice there is no x squared over here. This will have to equal negative 4, because that's the coefficient in front of the x to the first power. And the constant right here is negative 8. That's my constant, so that's going to equal negative 8. Don't forget, we already know this, and we can use that to our advantage. So just quick, you can double check whether or not we screwed anything up here by looking at this. 4a1 has to equal negative 8. Well, a1 was 2, Does -4 times 2 equal -8? Yeah, so that matches up with what we already found. But now we have some of this other stuff. Well, remember, if we know A1 and A2, then we can use that to find B because this whole thing has to equal 2. And again, if we know A1 and A2, we can use that to help us find C because we know this whole thing has to equal -4. And so this is how we're going to get B and C. It's not pretty. It takes a long time, but it is just algebra. Okay, so we had A1 plus A2 plus B equal 2. We also knew that A1 equaled 2 and A2 equal -2. So we plug that in here. 2 plus -2 plus B equals 2. These cancel out. We got B already. That was pretty easy. We also knew that 4A1 plus 4A2 minus C equal -4. Again, using this, we're going to figure out that 8 minus C equals -4. Well, those cancel, so C equals 4. That was pretty easy. And we got our B or C, and we could be on our way. But remember, there was one more equation in our equal parts that we didn't use, which was minus A1 minus B plus C equals 0. And I don't like to let anything go to waste, so I'm going to use this to double check to make sure I have all the right A1, A2, B, and C's, because if they are correct, they should work in every single one of the equalities we created. Well, A1 was 2, so this would be minus 2. B1 was 2, so this would be minus 2. And C was 4. Does that equal 0? Yeah, it sure does. Okay, so that makes me feel better that all our parts are correct. Now, remember, we have an integral still to do. Our integral was supposed to be the integral of A1 over x, so that would be 2 over x, plus A2 over x minus 1, so that's -2 over x minus 1, plus bx plus c, so that'll be 2x plus 4 over x squared plus 4. Now, this is the trickiest one of all. In that, well, I shouldn't say that. It's not that tricky. But this is a pretty easy integral. This is a pretty easy integral. We've done stuff like that already. This is the one I'm talking about. Well, we're going to have to integrate this whole thing. And you might right away go, use substitution. You don't have a u to u. What you do have is something that looks like kind of a combination of two things. Could be a u substitution if this 4 wasn't here. And you would have u and then du. But the 4 is there. Well, it also looks like an arctan if this 2x wasn't there. This is an arctan. Well, why don't we just split this up into two separate fractions? 2x over x squared plus 4 plus 4 over x squared plus 4. And this one could be substitution, and this one could be an arctan. That's totally legitimate. You can split apart numerators. You cannot split apart denominators unless you do partial fraction decomposition. And so now we're going to go ahead and integrate this. So now we finally get to integrate. And so I'm going to do the integral of 2 over x minus 2 over x minus 1 plus 2x over x squared plus 4 plus 4 over x squared plus 4 dx. So logarithm for the first one, 2 log x. Logarithm for the second one, 2 log x minus 1. This is going to be a logarithm as well, but because of u substitution, if I let u equal x squared plus 4, du is 2x dx, and so what do we get here? Du over u. That's a logarithm integral, so I'm going to get log of u, which was x squared plus 4. And finally, I have this one, which is your arctan integral. The 4 will come out, but then I get 1 over 2 arctan x over 2. Why? Because u is x and a is 2, And so this becomes u squared plus a squared. You could also technically do trig substitution, but arctan is so much easier. So a little bit of simplifying. All these logs can come together. This can cancel here. And we're going to get this 2 comes in, this 2 comes in, this one's being subtracted, so we divide. So we end up with, finally, log of x squared times x squared plus 4. That's this one times this one, because they're both positive and added together, so multiply. And then the next one would be x minus 1 squared, because it was subtracted, so we divide, plus 2 arctan x over 2, throw a plus c on there, and you got your answer. So what you see here is these problems can get long. And one thing I always say is that as you move through math, it doesn't necessarily get that much harder. The problems do get a lot longer. And so when you look at each step of this whole big problem we just did, individually, none of the steps themselves were all that bad. You should be able to handle each step individually. It's putting all those steps together and ensuring you don't make a mistake on any of them is the trick. And you make a mistake on one of those steps, everything after it is just wrong. And it's a waste of paper, essentially. Start all over. And you're going to see that as you move through math, if you go into Calc 2, differential equations, and so on. The problems don't necessarily get harder, they will get longer. So your need to be precise becomes even more important. Your need to get every little detail correct becomes that much more important. So something you really need to worry about. And I have students complain to me and say, well, I was only off by a negative. It's not that big a deal. Well, that could make a huge deal if that's the first step of a 50-step problem. So precision. That's what we're going to try and work towards. Okay, here's one more. I'm going to change it, though. I'm going to change it because I have a typo in this. I really wanted this to be an x squared. And so I look at this and go, okay, well, what am I going to do? Can I do a u du? Can I just get out of this with substitution, be done with it? Well, no. There's no part of this that is the derivative of the other, so that's not happening. What are my other options? Well, it is a rational function, so partial fraction decomposition is an option here. And this is something you're going to have to get good at. Every integral you see, you have to think about what are my options. What about this integral tells me I can do A, B, or C? So it's a rational function. Rational function tells me I have partial fraction decomposition as a possibility. Now what? Well, is it a proper fraction? That's your first question. Technically, yes. If this were to be multiplied out, it would be a fourth power. This is a third power, so the degree in the numerator is smaller, so I don't have to do any type of division first to get this thing going, so I'm going to leave it. All right, can the denominator be factored? Remember, this is an x squared. Well, it already is factored. It's factored as x squared plus 2 squared. So a lot of the work is done there. So now let's just decompose it. So 8x cubed plus 13x over x squared plus 2 squared is going to give me what? Well, I'm going to have two denominators. X squared plus 2 to the first and x squared plus 2 to the second. I mean, you might look at it and go, well, there's nothing I can decompose it into. Well, actually, yeah, because it's x squared plus 2 to the second, I build up to that power. I put the first power and then the second power. And so technically, these two denominators here could come together to give me this common denominator. And that's it. Those are the only two fractions I could add together to get me the common denominator. So this is the most I'd be able to expand it. And so what would the numerators be? Well, they're both quadratic, right? This is quadratic. This is quadratic as a factor. I mean, technically it's a fourth power if I multiplied it out, but the factor is quadratic. So b1x plus c and b2x plus c2. If you want to use all different letters, A, B, C, D, instead of B1, C1, B2, C2, go for it. All right. So I have to find B1, C1, B2, C2, and then hopefully I'll be able to integrate. And if you take a peek at it, think about what the integration might look like for all these pieces, we're going to be able to make it work. So anyway, we'll get to that in a second. Well, first thing we're going to do is clear the fraction out. So this is my common. So I'm going to get 8x cubed plus 13x equals b1x plus c1 times x squared plus 2 plus b2x plus c2 times 1, essentially. This is a common denominator, right? So if I multiply this fraction by that, it cancels. If I multiply this fraction by that, one of the x squared plus 1 plus 2's will cancel with this one, but it'll still be an extra one. And when I multiply this one by that, the x squared plus 2 squares cancel completely. So just give me this. All right. So now the fractions are cleared. Now what? Well, in the past couple examples, we let x equal something and go from there. But that was because the denominators were linear factors. We had some linear factors. These denominators are not linear factors at all. Okay, let me try and clear some of this out so you can see it. They're not linear factors. They're both quadratic. So that's not going to work. The only thing that works here is that equal parts idea. Again, we could set up a system of equations, which again could get fairly complicated. 4 variables, we might need 4 equations. We might have to then travel into something called linear algebra, and I think that's beyond us right now. So I think your best bet is to do equal parts. And so I end up with b1 x cubed, again I'm just multiplying this out, plus c1x squared plus 2b1x plus 2c1. And then I have a b2x and a c2. And I'm going to change colors. I'm not a big fan of this color. Okay, that's a plus. And on the left side, remember, I got 8x cubed plus 13x, right? So if I group by terms, I got b1x cubed. I have c1x squared. These two are both x, so I get 2b1 plus b2 x. And then finally I have 2c1 plus c2. Equating that to the other side, the coefficient in front of the x cubed here is an 8, so this coefficient has to be an 8. The coefficient in front of the x to the first is a 13. Here is the x to the first coefficient. That's got to be a 13. Now there's nothing else on the left-hand side, which tells me this has to equal 0, and this has to equal 0. So knowing that, I got, well, b1 equals 8, c1 equals 0. If 2b1 plus b2 has to equal 13, but I already found out that b1 equals 8, then that tells me that 16 plus b2 has to equal 13, which tells me that b2 would have to be negative 3. And finally, this here tells me that 2c1 plus c2 has to equal 0, and if c1 equals 0, then c2 has to equal 0. So if we place that back into the original piece here, we could then use that to integrate. So c1 and c2 are both going to be 0, so I can drop those off. And then b1 is 8, and b2 is negative 3. Now it's just a matter of doing that integral and finishing this one up. So we end up with the integral of 8 over x squared plus 2 minus 3x over x squared plus 2 squared. This is all dx. So I'm going to use the same substitution pretty much through this whole thing. Well, this one's going to have to be an arctan. This one I'm going to use U substitution. So u equals x squared plus 2, du equals 2x dx. I have 3x dx. Well, that's fine. Just take the x dx, right? Divide by the 2 and pull out the 3. You can do that. This one's arctan. If u equals x and a equals root 2, then here you got your a squared plus u squared. Pull out the 8. So I'm going to end up with 8 times 1 over the square root of 2 arctan of x over square root of 2 minus 3 over 2. Again, that's the 3 and the over 2 coming out. And this becomes the integral of what? Du over u squared, which if I bring the u squared up, which we've done this a bunch of times now, u to the negative 2 and integrate it, I would end up with 8 over square root of 2 arctan of x over square root of 2 minus 3/2 times negative u, which was x squared plus 2, to the negative 1 plus c. So clean that up a little bit and we're all done. 8 over square root of 2 arctan x over square root of 2. This will become plus 3 over 2x squared plus 2 plus c. And there's one where we had all quadratic factors, still were able to get it done. So like I said before, they are longer, but the whole purpose is to get us to the point where we're able to integrate. Your basic guidelines for doing this are really looking at two different possibilities. Either you had quadratic factors when you factored the denominator, or you had linear factors. And the linear factors, when that happens, what we're going to do is we're going to substitute the roots for the distinct linear factors to make them 0 and solve for our different components. If we have a repeated linear factor, okay, we're going to basically have to pick a random x value that's convenient with all the other pieces that we found, and then solve for the remaining coefficients. If we have quadratic factors, that goes out the window. What we usually do is we just expand the basic equation on the right-hand side, collect our like terms, do our equal parts method so that we can equate our coefficients to solve for a, b, and c, and then solve each one of those linear systems. Sometimes you have to do a combination of both of these because you have a combination of linear factors and quadratic factors. We saw an example like that. But really the factor in the denominator, whether that factor in the denominator is an x plus 1 or that factor in the denominator is an x squared plus 3x squared plus 3, really makes all the difference. In one, the numerator, this one should be a constant. This one should be a linear plus a constant. And how you're going to go solve the resulting equation after you clear the fractions will change based off of the fact that this was a linear factor or quadratic factor. Here, I would just let x equal negative 1, and then hopefully that'll get me what a1 equals. Here on this one, after I multiply everything out, I would have to expand, do equal parts because of the quadratic factor.